We talked about acid last time. So you also need to know what is base and alkali. So if you look at the word a base, so what is actually a base? A base is like a metal oxide or a metal hydroxide. So you can say a base is a metal oxide or metal hydroxide. A simple example could be copper oxide or copper hydroxide. It would be called a base. Zinc oxide, zinc hydroxide, sodium oxide, sodium hydroxide, magnesium oxide, magnesium hydroxide, copper, we said copper already, lead oxide, lead hydroxide. So all of these examples is going to be base. So they are called base. So what is the difference between a base and an alkali? So if you take any of these base, you take like one spatula of the solid, you mix with water, and you see that it dissolved, then it is an alkali. So if you have to define an alkali, you can say an alkali is a soluble base. So if you pick one of the base, you mix with water, and you realize that it dissolved in the water and give you a clear solution, for example, that would be an alkali. There's not many alkali, so I would say there's lots of bases, but very few alkali. The main alkali that you need to know is if you take, for example, sodium hydroxide and you mix with water, it will completely dissolve. So that's an alkali. So the most important example is sodium hydroxide. And the second one is potassium hydroxide. So these are the two alkali that we're going to use quite often in that topic. Now I'm going to show you the use of indicators on acid and bases, obviously acid and alkalis, and you will see the difference of colors. So when you take an indicator, so an indicator is a chemical substance. It is colored, or sometimes it is colorless as well. But as soon as you put it in an acid or an alkali, it will change color. And that color indicates to you. So let's say, for example, you have two test tubes, and one test tube consists of acid, the other test tube consists of an alkali. So you won't know, let's say, for example, both are colorless. So the main way of identifying which one is which, so you take an indicator, which I'm going to show you in a minute, and then you add in both, and the color change will actually tell you which one is an acid and which one is an alkali. So we're going to learn about indicator. We have three indicators that I'm going to show you. We can also use litmus paper. You're already aware about litmus paper. We have red and blue litmus paper. So I'm going to use this. And then there is phenolphthalein, which is colorless. We have methyl orange, which is orange. And the difference in color will give you a hint. So this is about it. And I'm going to show you also how to prepare a salt. So at your level, you should be able to describe how to prepare a salt. So I would advise you to watch the video of how to make a salt and write the procedure of making this salt. So step number one, for example, add 20 centimeter cube of the acid and so on using a measuring cylinder, as you did earlier at the beginning of year 10. So try to write the procedure because you need to know how to prepare a salt. Now, you also need to know whether a salt is soluble or insoluble. So for this, I'm going to give you a list of the soluble and insoluble salt, and then I'm going to give you another list, and you have to figure out from that list which one of these is going to be soluble and which one is going to be insoluble. Okay, so the list is all nitrates are soluble. So if I take, for example, copper nitrate, I take zinc nitrate, I take magnesium nitrate, or any metal nitrate, mix in water, it will all be soluble. So any nitrates will be soluble. Then if you take any sodium any potassium and any ammonium ion, they will also be soluble. So for example, sodium sulfate, sodium phosphate, potassium nitrate, potassium chloride, ammonium sulfate, ammonium carbonate. So any salt containing sodium, potassium and ammonium would be soluble. Then all sulfate are soluble. When you talk about the sulfate, the metal sulfate, they are soluble except for lead sulfate, barium sulfate, and if you talk about calcium sulfate, they are sparingly soluble in water. So when you say sparingly soluble in water, this word, we're trying to say if I have one spatula of calcium sulfate and mix it in water, half of the salt will be soluble in the water and half will remain insoluble in water. But if you take lead sulfate or barium sulfate, you mix with water, it will not be soluble. But take any other sulfate. Let's take magnesium sulfate, let's take sodium sulfate, let's take copper sulfate, they will be soluble. If we talk about chloride, all chloride are soluble except for lead and silver. So lead chloride and silver chloride will not be soluble. The rest will be soluble. Then all the carbonate, now just make sure you don't forget. So we were talking about all of them being soluble with exception, but for carbonate they are all insoluble, except we mentioned 3 of them, which will be soluble. So if I take copper carbonate, insoluble, magnesium carbonate, insoluble, potassium carbonate, or potassium is here, because all potassium are soluble. So this will be also soluble. Alright, so this is called the solubility rules, and when you're trying to prepare salt, it's a good idea to know about this, and this question comes very often in multiple choice, where you have to figure out if I want to do filtration, for example, and it consists of 2 different salts. If I mix them with water, one will be soluble and one will not be soluble based on this, and hence you can filter it off. So when you filter it off, the one which is insoluble remains in the filter paper as residue, and then the one which is soluble is going to drain through the filter paper and collect it as a filtrate. And then if you want to, you can actually just like heat off the water and get the crystals. So in a way, you can actually separate them based on the solubility of water, for example. Okay? So here I'm going to put the indicators. Here I'm going to put alkali, and the alkali I'm going to use in this situation is going to be sodium hydroxide. And here I'm going to put acid, and I'm going to add hydrochloric acid. Okay? Okay, so what I'm going to do is, let me put a few drops of hydrochloric acid, HCl, which is 2 mole per dm cube. So 2 mole per dm is quite dangerous. If it gets on your skin, after some time, 5 minutes, you can burn. So this is acid. And then the next one, I'm going to put sodium hydroxide. Okay. Now I'm going to use different indicators. So I have methyl orange, which is orange. I'm going to add here, this is methyl orange. Which is orange, and hence I'm going to add few drops of methyl orange in alkali and acid. Let's add in the acid first. So we say that the indicator turns pink when added to acid, and when the methyl orange is added to alkali, it gives a yellow color. So orange indicator turns pink in acid and yellow in alkali. The second one we're going to use is called phenolphthalein. Slightly hard to write down. It's written like this: phenolphthalein. This one is colorless, not very useful for acid though. Let me show you. So this is how it looks like. It's colorless. And then we're going to add in acid. It remains colorless. But then when you add into alkali, we also say that it becomes pink. Then the next one I'm going to use is blue litmus paper. Okay, I'm just going to tear off one of the page. I got this. I break it into two. I place both blue litmus paper, one in acid. It becomes red, and in the alkali it remains blue. So blue litmus paper, when you have blue litmus paper, in alkali it remains blue, but in the acid it turns red. If I use red litmus paper, I do the same thing again. If I put it in alkali, it's going to turn blue, and in acid it remains red. Then one last I want to show you is called the universal indicator. It's usually given like a piece of orange paper, and then we have some colors which state the pH value. So for example, if you can see it properly, if you have pH of 1, which is really acidic, it's red. If it is a bit less acidic, it becomes a bit more yellowish, and then it becomes green for water and more blue to alkaline solution. So you just need to remember 3 colors for universal indicator. We have the liquid version as well, but we also have paper. So if I use 2 P's like this, so I add in the alkali, it becomes blue, and the acid, it becomes red. So that was universal indicator. And this is litmus paper. So you need to know for RGCSE about, do we have water? Yeah. If I use water, for example, so this is water, add universal indicator, it should become green. So let me try to zoom it for you. I would suggest create a table. So in the table, you can create something like this. Let me show you. You can create a table. And in the table, you can, for example, here you write indicator, acid, alkali. Then you name the indicator methyl orange, phenolphthalein, litmus paper, and then you write down the colors for acid and for alkali. Yeah? So here you write indicator. Then you name the 3 indicators we just talked about, these ones. Here you write acid. You write all the colors of the acid in the based on the indicator, and here you write alkali, and then you write all the colors based on the indicator. So let's say I want to prepare the salt calcium chloride. Okay, I need to figure out which acid I can use. If I need chloride, I need hydrochloric acid. as one of the chemicals that I'm going to add. Then I need something based on calcium. I'm not going to just use calcium, but I can use calcium oxide and hydrochloric acid, mix it together. Or instead of calcium oxide, I can use calcium carbonate as per the previous video. Okay, so I'm going to use calcium carbonate. So I've got some calcium carbonate. So this is my calcium carbonate. So I'm going to use this, which are white solid, powdered, and then I've got also, so this is my calcium carbonate, and I have also hydrochloric acid, so HCl. So I'm going to mix both together, and then I'm going to filter the excess of calcium carbonate because I'm going to put this in excess. And once I filter this, I'm going to get my filtrate, and then I'm going to evaporate my filtrate to get the salt of calcium chloride. Okay, so I'm going to do the practical for you to see how to do it. And based on this, you're going to create a science report, which I'm going to guide you further in the instruction. Okay, alright, so let's start. So how to do it? We're going to take a beaker. So we take a beaker. Okay. In that beaker, I'm going to place some hydrochloric acid. So let's say I measure 20 centimeter cube by using a measuring cylinder. So I use a measuring cylinder, measure 20 centimeter cube of hydrochloric acid, and put it into the beaker here. Alright, so I'm going to do this. This measuring cylinder is only 10, so I'm going to do 2 times. So this one, so 1, and then 2, I have 20 centimeter cube of my hydrochloric acid in there. Okay. Now I'm going to put 1 spatula of calcium carbonate. Remember, I can also use calcium oxide. So I'm going to add 1 spatula of calcium carbonate. There's a reaction going on. Now because I'm using carbonate, that's why you can hear the fizzing. Carbon dioxide is coming out. If I want to speed up this chemical reaction, I can actually heat the mixture. I add 1 more until there's no more effervescence. I can hear only tiny amount of fizzing. I think the reaction is complete, but I would put excess. Yeah, I can't hear any fizzing. So now I'm sure there's no more further reaction in this one, and I'm sure that my calcium carbonate is in excess. And hence, my hydrochloric acid, we use the word limiting reagent. Limiting reagent means if this one is in excess, then this one becomes a limiting reagent. Means it's completely used up. Okay, for this particular one, we don't need to heat it. The reaction is quite complete. But if we use others, I would say to be on the safe side, we heat a little bit to ensure that the reaction has been completed. Then, as you can see here, we have white solid in it. So what I'm going to do, I'm going to filter this using filtration. Okay, how do I do filtration? I take a piece of filter paper, I fold it into half, making a semicircle. I fold it again once more, and that makes a quarter circle. Okay, now I just need to open on one side. So you can do it two ways. So you can either on one side or you can open it on the other side as well. Okay. So let's say I open it and only this doesn't matter really. So then I'm going to place it in a filter funnel. So that's my filter paper. That's my filter funnel. Okay. So then I'm going to use a conical flask. So this is a conical flask. So I'm using this because I can hold my filter funnel onto it. Okay. So now I'm going to pour out this solution and the extra of calcium carbonate in there. And we wait for a while. So what I'm waiting for all of the solution, so calcium chloride solution, to run through the filter funnel and the filter paper so I can collect it here. Now there's two key terms that you need to know. Whatever runs down through the filter funnel and the filter paper, whatever is here, is called a filtrate. Filtrate, filtrate. And whatever remain on top here, which will be the excess of calcium carbonate, is called the residue. RESIDUE, residue. So these two key terms are really important for filtration. So always when we do filtration, we have a residue which where the solid is going to trap in the filter paper and the filtrate is going to come down. Now, whatever is trapped here is our excess calcium carbonate, and whatever is going through here is the product. So the product is calcium chloride as well as some water and the carbon dioxide already escaped. Remember the fizzing? Okay, so we are waiting for all the filtrate to be collected, and once we get this, we can actually evaporate the water to get crystals of calcium chloride. So I'm waiting for it. In the meantime, I'm going to look for my setup. So there, let me put it here easier. So my setup would be to use a Bunsen burner, but I don't have a Bunsen burner, so I'm going to use this. So yeah, I don't have a Bunsen burner, so I'm going to use this, okay? It acts exactly as a Bunsen burner, but the most important thing is to have this. It's a bowl, it's called a crucible. C-R-U-C-I-B-L-E, crucible. A crucible is a heat-resistant bowl where we can actually put our filtrate in there, and it is heat-resistant, so it will not break when I'm going to heat it. So I'm going to heat this up and evaporate the water from the filtrate. So this is why I'm going to put it on top here. So I'm still waiting to collect all my filtrate. As you can see, they are colorless solution. It doesn't need to be colorless, it all depends like what the salt is. So if it was, for example, copper sulfate would be blue, but this one is colorless, okay? So we're still waiting for all of the solution, all the filtrate to drain. So that's fine. And we can see the filtrate coming down. This is clear, colorless solution. And we have to get crystals out of it. We want to get the salt out of it. We want to get calcium chloride salt from this clear, colorless solution. And if you can see on the top here, it's the excess of calcium carbonate that we can see. Now, as you can see, it's quite white, so it's a bit hard to see. But all the salt, it has been completely dried now. So I'm going to just add some water to wash the salt and make sure that I have my maximum amount of calcium chloride that I produced in that chemical reaction, right? Okay, so this is being washed. Now I'm going to fast forward this. Okay, so this is my filtrate. Okay, in a minute I'm going to show you the residue, how it looks like. Okay, but we don't need it anyway. So I'm going to pour out the filtrate in the crucible. Alright, so that's all of my calcium chloride solution in here, and I want to get the salt, the crystal. So I'm going to put it on my Bunsen burner. I'm heating it up. If you want to have a closer look. So I'm heating up the crucible so that the water can evaporate from the solution, leaving behind the calcium chloride salt. But I'm not going to heat it up completely to evaporate all the water. I'm just going to evaporate until there's only few drops of water in the crucible, and that's called a saturated solution. Now, as you can see, it's boiling. So the water is evaporating slowly and slowly. This process takes slightly a bit of time. Now I'm not going to allow all the water to evaporate because I don't want the salt to be exposed to direct heat. If all the water evaporates, that will decompose the salt, means the salt will be converted into something else. Okay, so my aim is to evaporate the maximum of water from it. Okay, I just want only a few drops of water to remain in my crucible with the salt. So we're waiting for that saturated solution. SATURATED, saturated solution. We need that key term. That's really important. Okay, so we're still waiting for it to get evaporated. We have to make sure that we are observing until there's only a few drops of water. We can see on this side a little bit some salt being formed here on the edge of the crucible. Okay, I'm just going to turn off the fire. Now this is a saturated solution. There's only 3 drops of water in there. I'm going to scrape it out so you can actually see it. So I've got a new filter paper. Oh, I need a test tube holder. Okay, this is a tong, T-O-N-G. So I'm just make sure that you know all the words. So that's called a tong. T-O-N-G, and I can hold this using the tong. So, for example, here like this, because it's really hot. Then I'm going to scrape out the solid. So the water, the tiny drops of water has already evaporated. We have quite some salt in there. So what I'm trying to collect right now is crystals of calcium chloride. So let's show you. So these are the crystals of calcium chloride, which I tried to get from calcium carbonate and hydrochloric acid. So now I've got my salt, I've got my crystals, and I can use it for other things, which I want to. I talk about acid. I describe acid as a proton donor. If you still remember, proton donor means they're going to give H+. Then who accept them will be the base. So the base is going to be a proton acceptor. Or you can write O as well. Let's take a simple example. So let's say, for example, we have H+, which comes from an acid. You react it with a base. A base is OH minus. So the OH minus is going to accept the H+, forming H2. And this equation here, as you can see, is called neutralization. Neutralization means that imagine that H+ was really dangerous. OH minus is dangerous as well. In the two extremes, they're both corrosive. They will react together and neutralize each other. So at the end, you have only water, so it's completely safe. So let's say this is super corrosive and that one is super corrosive. So they kind of fight with each other. We call it like neutralize each other. And at the end of the day, we have like only water. But if we take, for example, let me take an example like an acid would be, for example, hydrochloric acid. Then we react it with, let's say, sodium hydroxide. We did this before, but we never emphasized on neutralization. So this is the base, obviously alkali, and this is the acid. You already know that hydrochloric acid, the chloride, has become sodium chloride. Plus, because we have hydroxide, we end up with water. So when you look at this equation, you know that this is an acid reacting with an alkali, acid reacting with an alkali. Alkali always have OH minus, and this is what gives alkaline properties. So when they react together, they get the salt, which is neutral. Sodium chloride is stable salt, you actually can consume it, and you have water as well. So they were both corrosive individually, but then when they combine together, they neutralize it into something which is very safe. So in a way, you're going to get like salty water at the end, which is neither acid nor alkaline, and this is called neutralization.